Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, today in this particular lecture, we will be solving some typical problems using Castiglione's theorem. Already Castiglione's theorem we have covered a little bit earlier, and after that we solved several things using, considering instability, unstable equilibrium or the instability in the column buckling, right. So, that is thing we have already covered in the last lecture. Now, this lecture I am thinking that I will give some more numerical examples using Castiglione's theorem, so that you will understand the powerful technique, okay, of Castiglione theorem. Okay. So, let us solve this kind of indeterminate structure using Castiglione's theorem. What is that? So, I am applying one force P, okay. This is A, this is B, total span of the beam is say L. Our objective is to find reactions at C, where this is your A, this is your B point, this is your C. This is completely indeterminate structure. You cannot solve this kind of problem using only statical equilibrium equations, as you know. And this problem was solved by previously it was solved by using your method of superposition, and there you know the solution, right. And let us see whether we can get the same solution using Castiglione's theorem or not. Okay. So, if I remove this support C and if I replace the support reactions and replace with the support reactions, then how it will look like? The beam will be a cantilever beam which is carrying a load P here, and the support reactions will be something like RC and say MC. These two are not known to me, these two are unknown, but as we know from our support condition, that is fixed support will provide one force as well as one moment, right, fine, as we know from our earlier discussion. Now this is very simple to solve by using Castiglione's theorem, right. So, we are considering two sections to define the whole problem. So, one section is here. So, this is section 1 say, and this is section 2. Okay. Now, if I want to solve this beam for section 1, I can draw the free body diagram like this: RC, MC, and here you have MB. This is the length say L minus x. Okay. So, for that you can calculate MB equal to RC into L minus x minus MC. Fine, no problem, up to this no problem. Then for section 2, what we are doing? This is the section 2, you have MB, this length is L minus x, this end you are having RC, MC moment, and the force here, right, say P. Okay. This is your say P. Okay. So, for that I can get the expression for MB equal to RC into L minus x minus P into L minus X minus B minus MC. This is the expression for MB. And as we discussed in the previous lectures, that we will not be considering the contribution of shear force, okay, in the deflection calculation, because that is negligible. I mean, the strain energy computed based on shear force will be negligible as compared to the strain energy coming from the bending moment. That already we have discussed, okay. So, we are neglecting that part. So, this is the expression for bending moment. Now, if you want to find out delta C, that means the vertical deflection at point C. That is the vertical deflection at point C, fine. So, that will be simply given by, as we know, MB by EI, okay, del MB del RC, because some concentrated force is acting there. So, we can take the partial derivative of the strain energy with respect to that force RC, and that will give me the deflection. So, del MB del RC into dx. So, now we can write here 1 by EI, because EI is constant for the whole beam, A to L, okay, RC into L minus X minus MC, that is coming from section 1.1, okay, into L minus X into dx. Del MB del RC for section 1.1 is L minus X, that you can check from the expression of MB, fine, plus 1 by EI 0 to A. Now, this is coming from section 2.2, RC into L minus X minus P into L minus X minus B, that is given here, minus MC, and del MB del RC is simply L minus X into dx, fine. So, this can be further written as 1 by EI A to L RC L minus X whole square minus MC into L minus X into dx plus 1 by EI 0 to A RC into L minus X whole square minus P into L minus X minus B into L minus X minus MC into L minus X into dx. Now, you do the integration. If you do the integration, basically you will be getting the expression like that, delta C equal to, if you do this integration, you will be getting delta C equal to minus 1 by EI P B cube by 6 minus RC L cube by 3 plus P L cube by 3 minus P B L square by 2 plus M C L square by 2. Okay, got it? Now, what is the actual value of delta C at point C? It is simply 0, because that is the fixed support. In the physical problem, your delta C, because we are taking out the support and we are replacing the support with our support reactions, that is fine. We have got delta C, but ultimately or eventually your support condition will give you the restriction, right? Delta C must be 0. right. If you put this 0, then basically if you put this 0, then basically you will be getting one equation like this, mc L square by 2 minus RC L cube by 3 equal to P into B L square by 2 minus L cube by 3 minus B cube by 6, say equation 1. Fine. So, you have got this equation by putting delta C equal to 0. Now, what we can find out similarly, I can find out phi c. What is phi c? That is the rotation at point C. Now, how we can find out? We can find out the rotation at point C by taking the partial derivative of the strain energy with respect to the moment which is applied at point C, and already some moment is applied, that is mc already is applied at point C. Therefore, I need not to consider any fictitious or some different kind of moment, right. So, already that moment is applied. So, I can simply write down mb by ei, okay, del mb del mc dx, that gives me the rotation at point C. Now, if you write down this expression, this equation, then basically you will be getting a very similar expression like your deflection delta C. So, basically you will be getting phi c equal to 1 by ei a to L RC into L minus x minus MC, okay, and del MB del MC, if you look at for section 1 that will give you minus 1 into dx plus, that is for section 2 0 to a RC into L minus x minus P into L minus x minus B minus MC, and del MB del MC for section 2 is again minus 1 dx. So, if you perform this integration, you will be getting phi c equal to 1 by ei mc into L minus RC into L square by 2 minus PBL plus PL square by 2 plus PB square by 2. That is the expression of your rotation at point C. Now, what is the actual value of the rotation at point C? Simply 0, because that is the fixed support and you cannot get any rotation, right. So, again this must be 0. So, if you put that equal to 0, then you will be getting another equation which will be looking like, which will be very similar to this, that will be MC L minus RC L square by 2 equal to P into BL minus L square by 2 minus B square by 2. This is equation 2. Okay. So, you have got two equations by putting delta C equal to 0 and phi C equal to 0. Now, if you solve this these two equations, then you will be getting RC equal to 12 into P by L cube B cube by 6 plus L cube by 12 minus B square L by 4. right. You will be getting from the solution of these two equations. RC is given by this. So, this can be further simplified as P by L cube. Instead of B, I can write L minus A whole cube by 6 plus minus this B square L, I can write L minus A whole square into L by 4 plus L cube by 12. So, I am just removing B from here in this expression, and I can write like this, and ultimately I will be getting RC equal to P A square. If you do further simplification, you will get 3L minus twice A by L cube. Can you recognize this expression? Already we have got this expression by using method of superposition, right? The same thing we are getting by using Castiglione's theorem. Only thing is that you have to, just you replaced the support by providing the proper support reactions, and then finally you made those things like your delta C and phi C equal to 0 simply. Then once you got RC, you can find out MC also from either equation 1 or equation 2. So, MC will be coming as equation 2. If you find out MC, MC will be coming as P A square L minus A by L square. That you can check it from equation 2 say. From equation 1 also you can find out that, that is a very simple thing. So, this is your MC value. Can you recognize this? You have got this expression earlier also by using method of superposition. So, this is the way you can apply Castiglione's theorem to solve the indeterminate structure. Now, at this moment you can find out the support reactions for indeterminate structure as well by using method of superposition or using Castiglione's theorem. Now, I will stop here. So, with this basically I am concluding this course. I hope that you have enjoyed, and this course, as I told you in the very initial lecture, that this course is very, very fundamental and conceptual. So, the understanding of this course will be really helpful for any civil engineer, mechanical engineer or aerospace engineer. And once you know this basic course basically, then based on that actually most of your theories in these engineering fields are established. Thank you very much.